Okay, well, thanks for inviting me to this workshop. Yeah, actually, I attended the last edition 5 years ago, which was in a nice place, Les Houches, and now, unfortunately, we can just attend virtually in this new edition. So before I start with my talk, a short announcement. Will be moving to a new position pretty soon, towards the end of the year, and I have a few positions available, like especially PhD and a postdoc position. So if you are interested, just reach out to me and we can discuss more. So when I did my postdoc with Yuri, I mean, one thing I still remember quite, or that somehow shaped my future research, was Yuri was always saying, every algorithm belongs to a problem class. Or for every problem class, we have to develop or find the correct algorithm. And while in the talk on Monday from Yuri, he presented different problem classes and the right algorithms. And this talk is a bit different because basically I start with an algorithm that is given, and basically the quest is to come up with a good problem class where this algorithm works well. So I will explain in a few minutes. So what is the broad topic we are working on? We are working on machine learning problems or optimization for machine learning. We have seen a lot of very great application of machine learning in the last few years, and there's been a very huge progress that has been made over the past 10 years. And I mean, one application of these machine learning algorithms I really like is that you can now quite easily translate a lot of text from different languages, and the quality is typically quite good. So I find this really useful. Of course, I cannot check if this translation here is correct or not, but to some extent I trust these algorithms. And so very brief, what we are doing, often we formulate, we want to solve a task. We formulate this as a learning problem. So we are given a lot of data, or we collect a lot of data, and then we want to train our machine learning model. And one way to formalize this machine learning pipeline a bit in an abstract way is we can think of, we want to solve an optimization problem that is given to us in stochastic form. So we want to minimize the expectation of a function that is unknown. So we call this the loss function. And okay, the function is known, but the data distribution is in general unknown because we cannot query every possible sample in the world. We can just collect a subset of the data. And what we can do, or typically assume, is that we can have access to stochastic gradients. So for instance, we pick one data sample and compute what is the loss, what the gradient of the loss function with respect to this single data sample. I'm now turning very quickly back to the optimization point of view. And just to summarize a bit, I mean, in deep learning, we typically have very, very high dimensional problems. So the newest model, I mean, the model sizes keeps increasing exponentially in some sense. And I mean, there are even models with trillions of parameters have been proposed. So how can we even expect to have an algorithm that converges on such a large dimensional problems in relatively few number of iterations? Moreover, these problems are typically non-convex, non-smooth, but what helps a bit is that they are over-parameterized, so that there's so many parameters that we can always find good solutions after training. And what is the algorithm that is used? So that's a bit of simplification. Most algorithms that are used are based on stochastic gradient descent, which is a very simple idea that we take a uniform sample of our data, or a mini batch of data samples, and then we compute the step towards the negative direction of the gradient of the loss function. And here gamma is a step size parameter. So in practice, it's very important to use variations like momentum or automatic step size tuning, or in particular tuning of the step sizes and so on. But in this talk, I will focus on stochastic gradient descent. Just maybe before we go into more details, a little bit of background on SGD, such that we all know that we are on the same page. When we analyze an algorithm, for instance, SGD, we need to define a problem class, and very standard, we assume that we have functions that are smooth. So the gradient is Lipschitz. And because we query stochastic gradients, we can assume a bound, or we assume a bound on the variance of the gradients. And of course, these assumptions can be relaxed and different settings can be studied. But it's a very old algorithm and also appeared in Arkadi's book, so it's nothing new on this slide. If you want to now analyze the convergence of stochastic gradient descent, well, it's just a 3-line proof, basically. We first used as our assumption that the function is Lipschitz. We can plug in this equation the step that we do, the SGD update. When we take now expectation, then just by our assumption that we have an unbiased gradient, we get here the gradient in expectation. And by our assumption on the variance, we can upper bound this second moment by the expectation squared plus the noise squared. And choosing now the step size small enough, we get a sort of a decrease proportional to the norm of the gradient. We can now rearrange this inequality a bit, and typically we average over all iterates. You get that's just you get by averaging this equations. So we now have an expression that depends on the step size, and we can now choose the optimal step size to get a convergence guarantee. So we see how this our estimate of the error decreases in big T, the number of iterations we do. So this is the kind of convergence rates we can prove for stochastic gradient descent. So to summarize, this is exactly the same results as from the slide before. We have on L smooth functions. I've just shown that we have that SGD finds a stationary point with accuracy epsilon after sigma square over epsilon square, L over epsilon stochastic gradient computations. And actually, it can be shown that this, I've just given 2 recent citations. They're probably older works that address the same problem for SGD, that this rate is optimal. So if we don't make any stronger assumptions, we cannot improve over this convergence guarantee. What very common in recent years is that maybe, for instance, assuming higher order smoothness or smoothness of the components or combinations or variations of these assumptions, and then these bounds can be improved. And of course, SGD can also be analyzed on convex functions or strongly convex functions, and I just give here the results for reference, but we don't really need to know them for this talk. As a small remark on convex functions, SGD is not optimal because we can accelerate the SGD with a more or less the same acceleration technique as developed by Yuri, and then we can actually accelerate this last optimization term. Okay, let's go back to what can we now do with these convergence guarantees. These convergence guarantees just say SGD will converge to a stationary point. And I've drawn here a picture of a function. We have 3 stationary points, And this convergence guarantee does not tell us to which of these stationary points we will converge. Moreover, also this rate, this sigma square over epsilon square is a bit over pessimistic, because if we know that we converge to this stationary point, then locally we can prove much faster convergence rates. And similarly, if we say we converge to this local minima, we can prove faster rates. So somehow this, or in my opinion at least, these convergence guarantees that we have for SGD on non-convex functions are not satisfactory in some sense. But I don't know, we're maybe analyzing the wrong thing, or we're using the wrong technique. Because SGD is in practice behaving much better than what this worst case guarantee would give us. So for instance, take here an example of a paper from Robert Kleinberg and co-workers. And they did the experiment of the following form. They run stochastic gradient descent 100 times, initialized at a random point on this interval, and they just simulate the stochastic gradients by adding Gaussian noise to the correct gradient. So if you run gradient descent, then we observe what we somehow would expect. We converge just to somehow the closest stationary point. So these red points are the points where gradient descent, where the last iterate converges. And here on the bottom is sort of a histogram where these last iterates converge to. But as soon as we add a bit of this artificial noise, SGD starts to behave much more favorable, because we see that it starts now to most of the iterates converge now to the local minima that is really a global minima of the function. And when we increase the level of the noise, it starts to look even better. But if we add too much noise, then we spread out again. And I found this very motivating and interesting. Can we actually prove that the stochastic noise helps SGD to really escape subtle points or local minimas that we do not want? And also from the same paper, they present basically the following insight. They say, in the experiments, we considered SGD on a function f with a stochastic gradient oracle of this form. So we can write down the iterates. So xt plus 1 is xt minus the step size times the true gradient minus the step size times the stochastic noise. We cannot just define new variables, y of t, which are defined in the following form. And then we can just rewrite the whole iteration now in terms of yt instead of xt. And we get the first line of equation. And if I take now expectation over the stochastic noise, the stochastic noise disappears because the expectation is 0. And we see that in expectation, SGD is doing gradient descent on the smooth function fw, which is just the function f convoluted with the noise xi. So, I mean, this is not a rigorous proof saying SGD is really doing gradient descent on the smoothed function, but this gives a heuristic argument or intuition that maybe there could be some relationships that we can prove. So this gives us a motivation to study optimization on this artificially smoothed function fw. And what I'm presenting now is based on some ongoing work with a master student of us, and I hope the paper will be available in a few few weeks or so on my website. So what are we studying? Well, we start with a very simple algorithm which we call smooth SGD. So we are given stochastic oracles, the same as for the normal SGD. And then the algorithm that we consider is we sample first sort of a random smoothing parameter, like a random shift. We compute the gradient at this shifted point, and then we update according to this gradient at this shifted point. So, okay, why do we call this smooth SGD? Well, in the case where this smoothing distribution is just, if we don't do any smoothing, so this U is always 0, then we just recover the normal SGD algorithm, and nothing has changed. So in case where there is no stochastic noise, so our oracle returns always the exact gradient of the function, we recover something called the smooth gradient descent. So it's just a gradient descent on the smoothed function. Yes, and in order to understand this connection between smoothing and SGD, what we actually would like to study is we want to smooth with the SGD noise distribution. So instead of taking an artificial distribution U, we would like to plug in what happens when we smooth with the natural gradient noise. But before we do this, we study somehow the impact of this smoothing by U and the gradient noise separately. And there are a few related works. So on the bottom, I list a few papers that also study the optimization on smoothed functions. So please check them out. And somehow the most closest related works to what we do is there was a paper by Hassan and this Kleinberg paper I mentioned before. And in summary, these papers make somehow quite strong assumptions. They say they consider smoothing with a for instance Gaussian distribution, but then they make the assumption that no, the function after smoothing becomes convex, which is a very strong assumption. So I mean, or in Kleinberg they assume some sort of star convexity. And this is a strong assumption we somehow do not want to make. To motivate a bit the type of functions we are considering, we want to study functions f that can be written as a sum of somehow a nice part, which we call g, plus some sort of perturbation h that is just adding the non-convexity and is a bit the difficult part that we have to control. So as a motivation, consider the function x squared plus x times sine x, which I plot here on the left. We can write this very naturally as a sum of a strongly convex function x squared plus this oscillation coming from x times sine x. So of course this would be a very strong assumption if we would need to assume that we know how g and h look like, because then I mean we can just optimize g and we are done. So we assume that we do not know this decomposition, we can only access gradients of f. Yes, and somehow the intuition is that after smoothing, there's a additional perturbation or this noise introduced by h that becomes much smaller and can be controlled. So more concretely, to maybe study the smooth SGD algorithm on this problem, we need a few assumptions, and in a few works, it was very common to assume that when we do smoothing, we should assume that the smoothing is unbiased and that the second moment can be bounded. So this can also be relaxed, but this is some of the most standard assumption. If we would have this, then we can also rephrase a bit what could be a good assumption on the structure that we need to make. And we assume that, there exists this structure, F is equal to G plus H. And there exists parameter big delta and small delta, such that the difference of the gradient of the smoothed function minus the gradient of G, the nice part, can be upper bounded by a constant delta plus some term relative to the norm of the gradient of G. And for instance, if we have a convex function G, then we can just define the delta as somehow the maximum over the set of the minimizers of G, so where the gradient of G is 0. And of course, this can also be relaxed. We do a small change. So when we want to analyze what happens, we also need the assumption on the stochastic noise. And we could now use the standard assumption that the noise of the stochastic noise is bounded by some sigma square. But we found it's very natural to consider sort of a joint assumption. So we just formulate a condition saying that if we do perturbation by smoothing and stochastic noise, we want to bound the variance by parameter sigma square, which corresponds to the stochastic noise, plus L times zeta square, which is the noise from smoothing. And essentially, under the standard assumptions, we can always recover this. So, and it's somehow the natural thing that will appear in the proof. Just now, illustration. I think that I mentioned this before, but then did not show it in pictures. We again have the same function from before, and I just plot here what happens if we do Gaussian smoothing. So in blue is the original function, and when I do smoothing with larger variance, then we see that the noise decreases and the function becomes not convex because it has still these bumps, but it has a very nice structure. So what can we prove? So under our set of assumptions, we can prove that the smooth SGD algorithm will converge to a stationary point of G. And the convergence rate that we get is essentially the same convergence rate as for standard SGD, except that we now are not stuck at the stationary points of F, but we can prove we converge close to stationary points of G. So for instance, if we can find a G that just has a one single stationary point, then we know we will converge to this unique stationary point. And for this, the function G does not even need to be convex, so we can don't need this assumption and observe that the convergence rate depends just on these two parameters jointly, and that's why we merge them into the same assumption. Okay, a small caveat, we cannot converge to arbitrary high accuracy. So especially if the big delta parameter is larger than 0, then we can just converge to a neighborhood of this stationary point. We can forever, we can make arbitrary assumptions on G, and basically what we can do, we can get convergence rates that just depend on the property of G, and we can somehow extend this. So for instance, when you would assume some strong PL condition, we can get a linear convergence rate to the neighborhood of the stationary point. Or if you would assume G is strongly convex, and so on. So I think that there's nothing too much technical there, which just you have to write down what you get. a very small comment how we can prove this. So actually we don't have to do much work, because there is another workshop paper we had with other master student last year, where we analyze stochastic gradient descent with biased oracles. So there's been a work by Yuri and his student also on gradient descent or SGD with biased oracles, and there's just a small difference on what assumptions we make on these oracles. So basically we assume that we can query stochastic gradients, but they are in expectation biased. So there's an expectation we do not get the gradient. And then we just consider the algorithm that now updates the sequence with these biased updates. And remember, the SGD proof I showed a few slides before depended crucially on the property that we get unbiased estimates. But this is not really required in the proof. No. So to summarize, we assume we have this biased gradient estimators. If we can control the bias by inequality of this form, so you remember this is exactly the same form as we used before, then we can prove a convergence of this biased SGD to a neighborhood of the stationary point. And this should be nabla F, so this is a typo. I mean, how does the proof work? Well, there's actually not really much to change. We write down that the same inequality as before. So the first inequality follows by smoothness. Then we take expectation, and now in this case, the expectation does not give us the gradient, but it gives us this bias vector. It should be bold B's, sorry for that. And then it's just sort of rearranging these equations. It's two lines, it's very simple. And then we can get a decrease condition of the same form as before, just that our decrease now depends still on the gradient norm of F, but is impacted by a factor 1 minus a small delta. So as long as this term is positive, we get a decrease, and the same proof from the slide before will work. Okay, this was a short deviation, and just how we can prove that this kind of algorithm converges. So what do we have now? So we have studied the smooth SGD, and whenever we add the smoothing ourselves, so sort of artificially, we add this perturbation, then we know that we converge at least, I mean, okay, we can always take the G function just to be the smooth version of F, and without any, I mean, this works in every case. We can take big delta and small delta equal to 0. Then it follows that smooth SGD can only converge to stationary points of the smooth function F mu, but not F. So this is already an improvement of what we had before. And remember, from the convergence rate depended only on this this combination of the parameters sigma and zeta. So we get the same convergence rate as for normal SGD, as long as we do not choose the smoothing too high. So if the smoothing is somehow controlled by sigma divided by L, we don't even converge slower. We just converge to better points. Okay, but even we could now think, oh, this picture is maybe already the smoothed version of the function F. So in this case, the convergence to stationary points of the smooth function does also not help us, because we are again stuck at one of these 3 stationary points. But in many cases, we can now construct a much simpler function, for instance, again, a quadratic function that now sufficiently well approximates our noisy function F, and then we can prove that we converge to the global minima in this case. what you have not shown is that there is really an equality between this SGD is exactly doing the same as this smoothed gradient descent. But from the argument from this Kleinberg paper, we would expect that somehow there should be an equality if the noise that we use for the smoothing is step size times the noise of the stochastic noise. And if this relation holds, we would expect some similar behavior. We did here some simulation on the same function that we considered before. And exactly, in red and green, we see the true trajectories. One is a normal SGD, and one is this gradient descent on the smoothed function. And they behave very similarly. We did also some experiments on logistic regression function on the digits data set. And again, we see, oh, there is actually quite good correspondence. And so maybe this really holds. However, we also did some deep learning experiments. This is actually the case where maybe gave the whole motivation to look at this smoothed SGD. And there we notice a few differences. Okay, the issue is we have trouble to really implement, to really simulate this stochastic noise, we would need to compute the full batch gradient in every iteration, so this is not feasible. We approximate this by taking gradient over a large mini batch. And this is done in red. And we see that on the left, we see the training. Exactly, the training loss, which decreases no faster than SGD, which is the blue curve. But the test accuracy is no lower than for the blue curve. So this is a bit not so great. But if we approximate this stochastic noise by taking two samples, two stochastic gradients, we get an algorithm that's pretty close. But this is now, I think we need to work a bit more to really understand what is happening here. So a few comments on further extensions. So we can quite easily extend most of these convergence results to, there are many techniques already developed that we could just apply to this problem class, and this works quite well. And for instance, right now we just have assumed that we get for this joint bound on the stochastic variance and on the smoothing, we have a uniform upper bound C square. We can naturally extend this to have an upper bound that scales with the norm of the gradient of G. And if you're a bit familiar with the literature for SGD convergence results, it's very common to assume that the stochastic noise can be bounded by an inequality of this form, so a constant plus maybe something proportional to the norm of the gradient. But for non-convex functions, this norm of the gradient can be zero at many, many stationary points. So it's not really that much a relaxation. While if you take a convex function G, then this norm of the gradient is really growing. And I think that there's a significant difference in the type of problems that we can consider. Of course, we could now, depending on the properties of this nice function G, we can come up with all kinds of better or accelerated algorithms. But maybe the question is a bit, can we give a tighter characterization of the minima that we can really escape? No. On the picture, I always argued a bit vaguely. And having such a shorter or better characterization, this would be quite interesting. And of course, having this really proof that SGD is equal to this smooth SGD in some well-defined sense. So to conclude, and I did not go over time. Basically, the main message of the talk, I do not want to convince you that taking this F is equal to G plus H assumption is the only direction that we should consider. But we should maybe start to think about what could be good assumptions that really capture the behavior of SGD, that gives us good explanation what really happens in practice. And in particular, I think the interpretation that SGD is just following the gradient flow cannot give us these good explanations, because a gradient descent is always stuck at the stationary point. But we know SGD escapes most of these stationary points and even local minimas. So there's really something better to SGD, and we should work to maybe come up with good assumptions that it can explain what is going on. However, we should always be a bit cautious. I mean, adding more and more assumptions is maybe helpful for the theory, but we should not lose focus to actually we want to explain what happens maybe in deep learning, so we should also take assumptions that make sense in the deep learning setting. That's all of my side, so I'm available for a few questions, and just as a reminder, I'm looking for students, so if you know somebody or, I don't know, want to know more, just reach out to me. So, thank you.
Thank you very much. Let's thank the speaker. We have time for questions. Enough time. Okay, Roland, please.
Yeah, I have actually two questions. Could you go back to one of the first slides with the problem statement?
On this decomposed problem on the
with the examples, so it's still.
Let me go. I go to the very first.
Yeah, here.
Yes. Okay. Yeah.
No, the one before.
Yes.
Here. Yes.
Yeah. Yes. Yeah. Okay.
Do I understand right? This 10 to the power 12. It's not the dimension. It's the number of data for the deep learning problem. I mean.
No. There are really models that have this many. So, especially these language models for translation. This 10 to the 12 is maybe extreme case, but 10 to the 9 or 10 are really used and trained. So this happens.
So this is really the number of parameters.
Parameters, yes.
Oh, yeah. Okay, but that was just a small remark. But the main question is this resembles a bit the simulated annealing procedure. So have you thought about similarities?
Yes. No. I think that that's very related, and I think what they did in this, what Elad did in his paper is a bit related to that. They even consider some adaptivity. So they changed the smoothing parameter during optimization, and so they even adapt somehow. I mean, when they converge, they change this parameter. So I think in this sense, that's probably the closest relation to simulated annealing, because they also adapt the smoothing. In our work, we just considered constant smoothing, like also Yuri did in this last paper. But I think, the right way to go is to consider somehow adaptive smoothing, depending on how close you are on already to the maybe optimal solution. Yes.
Yeah. Okay. Thanks.
Thank you. More questions? Yes, Alexander, please.
Hello. Thank you for your talk. Could you tell, please, did you compare your variation smooth HD with another stochastic algorithms like Adam or another examples and other optimization algorithms on the deep learning task?
Yeah. No. Okay, that's maybe a reason why it is tricky. No, currently this plot here is just for SGD and not with Adam. So this is we hope maybe to provide more figures a bit later on. And okay, we need to. I mentioned at the very beginning of the talk, in practice, also SGD with momentum is used. And in this figure, it's actually we use just the standard training algorithm, which is a SGD baseline with the tuned parameters. And this algorithm uses this kind of heavy ball momentum. And so this could be also one reason why this interpretation of smooth SGD may be equal to SGD does not hold, because in the results I've showed on the theory part, we did not consider this momentum. So I think this is also an open question a bit. What is the correct way to add momentum to this smooth SGD if we want to keep somehow the same behavior as SGD? There's maybe another remark to make. So this last reference, I will upload the slides when there are links you can click on. They make a different claim. You know, they say they also consider some sort of perturbations, which is in our smoothing we evaluate the gradient at slightly different points. And they say, oh, we actually want to do these perturbations to behave differently than SGD, because they then present the algorithm that gives better generalization, has better generalization properties in practice. So their goal was to really come up with the algorithm that is different from SGD, while our goal was to somehow mimic exactly what SGD is doing, but it was maybe the truth is somehow in the middle, perhaps.
Thank you.
Thank you. More questions? So it seems there is no more questions. Let's thank the speaker again.